Hello everyone, welcome back to this physics mastery, and this is work for energy, second slide for us. Okay. So in this lecture series, what I'm doing is, you know that PYQs are very important to practice at this point in time, but there are too many of them. You cannot solve all of them. So my idea in this particular part is to give the best of those PYQs so that with a limited time, you'll get the maximum benefit. So make use of this, and I'm sure it will help you a lot in your final preparation. Okay, let's go on with the questions. Right. This is work for energy, work done question. The force F bar, x square y I cap plus y square j acts on a particle in a plane x plus y equal to 10. This is a plane in which it is work. So it's actually xy plane. The work done by this force during a displacement from 0, 0 to 4, 2 is. See, work done by a force is very important in various chapters, not just in this chapter only. And whenever force is conservative force, work done becomes very easy because it becomes independent of path. But when force becomes non-conservative, then you need to follow the path and specifically calculate it. So actually it is non-conservative force. So to check whether it is non-conservative or not, you can use this idea, dou y by dou fx by dou fy. Let me, so dou fx by dou y equal to dou fy by dou x if I get right, then it will be conservative force. So when it is conservative force, you can take any path between given initial and final point, you will get the same work done. But here it is not conservative force. You see dou fx by dou y, if you do, you will get x square, but dou fy by dou x will give you 0. So it is not conservative. So that means I have to follow the path and solve it. Anyway, so how do I solve it? Let's see. They gave the work done. Work done equal to integral fx dx plus integral fy dy from initial position to final position. Okay. So in that, let us calculate individually. First, looks like fy dy would be easy to calculate. Let me calculate integral fy dy because fy depends only on y. Integration would be easier. Y would vary from 0 to 2, y value. So that is integral 0 to 2 y square dy. It becomes y cube by 3 and then 0 to 2. So that is 8 by 3 you will get. That is one integration. Straightforward you get. You don't have to worry about that path there. Now to calculate the other component, integral fx dx, there we require the relation between x and y. That specific path we need to consider. So first let us substitute x is equal to 0 to 4. X square you keep as it is, but y will be replaced in terms of x. Y will be 10 minus x. We take that. So it is path specific. This particular part of work done will be path specific. So we'll have to do integration here. So 10x squared integration will be 10x cube by 3 minus x cube, x power 4 by 4. And 0 to 4, we are going to substitute x coordinate 0 to 4. So x cube, 4 cube is 16, 4 is 64. 64 into 10, 640. So 640 by 3 minus 4 4s are 16, 16 16s are 256. 256 by 4. This is what I have it. I'm leaving the calculation part to you so that we can cover more problems. So this is work done because of the fx component, and this is work done because of fy component. Net work done is the summation there. So so it's basically question is of non-conservative force. You have to deal with the path there. That's a concept behind it. Okay, let's move on. Right. A block of mass 25 kg is pulled along a horizontal surface by a force at an angle 45 degrees with horizontal. Okay. The friction coefficient between the block and the surface is 0.25. Okay. The block travels at a uniform speed. So uniform speed, they said, that means acceleration 0, net force 0. So we can use that. Work done by the applied force during the displacement of 5 meters of the block is okay. So let's draw the diagram. So you have the force applied at an angle 45 degrees. Okay. And obviously you will have normal reaction pushing it up because mg is pressing the ground. Because of mg, the block is pressing the ground. not directly, indirectly. And then there will be kinetic friction here because it's sliding. So you will have kinetic friction here. So anyway, net force 0 because it's going in uniform velocity, vertically net force 0, horizontally net force 0. So if I resolve this F in this direction, I'll have F by root 2 cos 45. In this direction also F by root 2. So F is no more. F has been resolved. Now vertical equilibrium, horizontal equilibrium, if you look at it, upward forces are N plus F by root 2. And that is equal to mg. So I can calculate N from there. That is mg minus F by root 2. So that is normal reaction for us. Now horizontal equilibrium, net force horizontally has to be 0. F by root 2 should be balanced by kinetic friction. F by root 2 should be balanced by kinetic friction, which is mu k into m. That is the second equation. So we need to solve these two equations. Basically, you take N from here and substitute here, and then we'll get F there. So what is that we'll get here? So F by root 2, that is the second equation I'm considering. Mu times N is taken from first equation, which is mg minus F by root 2. So if you take F terms one side, you have F by root 2 into 1 plus mu, and that is going to be mu mg. All right, so I require F by root 2 from there, and that will be mu mg by 1 plus mu. That is F by root 2. So that is first part of the solution. But they're asking you to find work done. Work done would be only that component of force in the direction of displacement into displacement. The component of force in the direction of displacement is F by root 2 only. And the displacement, let us say S. So that's about it. Okay. So we can substitute the expression there, mu mgs upon 1 plus mu. That will be the work done by the external force there. So you can substitute the values. Mu is 0.25. Mass is how much? 25 into 10, 250. Displacement is 5 divided by 1.25. That is going to be 5 by 4 basically. So 5 by 4 meaning 0.25, 1 by 4 cancels out. So 5 gets cancelled out, you will get 250 joule. Okay, so that is the work done by this. So basically it is Newton's law application and also work done. Very straightforward. A little manipulation you have to do, but you should be able to do this kind of problems by identifying the important steps here. So here normal reaction is changing. Normal reaction is not mg. It is changing because of the applied force. That's one important care we need to take. Okay. Right. Next problem. A pendulum is suspended by a string of length 250 centimeters. Mass of the bob of the pendulum is 200 gram. Okay. Bob is pulled aside until the string makes 60 degrees with the vertical as shown in the figure. After releasing the bob, the maximum velocity attained by the bob would be. So we have to calculate maximum velocity. That is what I need to calculate. When will the velocity be maximum? So I'll use conservation of energy because it's a simple vertical circular motion, part of vertical circular motion. So wherever it has got least potential energy, gravitational, it will have the maximum kinetic energy, and that's where you will have the maximum speed. That is going to be at the bottom. So this is where you will have the maximum speed. Okay. So basically from here to here, I'll use a conservation of mechanical energy. I'll use loss in gravitational potential energy equals to gain in kinetic energy. So this is a conservation of mechanical energy for you. I'll write it as COME, conservation of mechanical energy. So what is loss in gravitational potential? This height I have to calculate. So this is L, right? This is L cos 60, which is L by 2. And then leftover would be L there, L by 2. So this is mgl into 1 minus cos theta, basically. That's a formula. I'm sure many times you would have used this formula. And that is half m into v square minus 0, initially 0. So mass gets cancelled. Then v equals to root over 2gl into 1 minus cos theta. We can substitute the values and see what you get. Square root of 2 into g, we will take 10. L they had given as 2.5 meter, 250 centimeters they gave. 1 minus cos 60, that is 1 by 2. So that's what we have here. So this 2 gets cancelled. 2.5 into 10 is 25. Square root of that is 5 meter per second. So that's what you have. It's very straightforward. Conservation of mechanical energy idea. Okay, right. Next problem. As per the given figure, two blocks each of mass 250 gram are connected to a spring of spring constant 2 Newton per second or 2 Newton per meter. If both are given velocity v in opposite direction, then the maximum elongation is. So that velocity v they didn't mention. I think probably while taking the information, it is missing out. Let's assume v. Okay. In terms of v, we will do it. So when will you have maximum elongation? Maximum elongation, that is what we need to understand. So when maximum elongation is obtained, you will have minimum kinetic energy. And the motion of it, you know, it will be oscillating, right? So simple, they'll have a phase difference of pi. They'll go like this, opposite to each other. So when they go to their respective extreme position, that's where you have maximum elongation. All right, that's where you will have maximum elongation. At that moment, the speeds are zero. So whatever kinetic energy that you have here, whatever kinetic energy that you have here, half mv square into 2, when that converts into strain energy, that's where you will have the maximum elongation. That is at extreme positions. So I think that is all about it. So half gone. X max will be equal to root over 2m by k into v. This is what we have. You can substitute the values and it's very straightforward. So when will the maximum elongation be? At the extreme position. All right. And at extreme position, speeds are zero, kinetic energy is zero. That's the idea. Okay. Next. A small block slides down from the top of a hemisphere. So this problem is very, very famous. Very, very famous in every module, every study material, every book. You will see this problem. Very, very important. I'm sure you have seen it many times. And but it is in the exam also. They will ask again on the same idea. They will ask again. So anyway, so what is it? The height h at which the block will lose contact with the surface of the sphere is. Okay, let us assume that it is losing contact here. Now, what is the mathematical condition which suggests that it is losing contact? That's very important. So losing contact is a physical term, but that doesn't give an equation for me. I need to have an equation corresponding to that particular condition. So whenever it is losing contact, normal reaction has to be zero. I'm sure you might have heard about it, but remember it. Whenever they say losing contact, normal reaction zero. Normal reaction zero. Okay, if there is no normal reaction, what force is there on the body? Only gravitational force. Only gravitational force is there. Because of gravity only, it has been traveling like that. Subsequently, it is going to go in a projectile motion, like parabolic path. But up to that point where normal reaction is zero, it was going in a circular path only. So whenever the body goes in circular path, you will have centripetal acceleration and also tangential acceleration. So if you just go slightly before it losing contact, right, normal reaction will be almost zero and it was in circular path only. In that case, there must be a centripetal force and that is because of gravity only. You take gravity component in this direction, that will be mg cos theta. Mg sin theta is a tangential force there. How about normal reaction? At that moment, normal reaction is zero because it's about to lose contact there. So because of mg cos theta, it is going to have centripetal acceleration. mg cos theta equals to mv squared by r. Okay, very good. I want half mv square from here. You take r this side and multiply with half. So you will get mgr cos theta equals to mv squared by 2 half. So this is equation 1, right? Centripetal acceleration concept there. Okay, now I want to use mechanical energy conservation of mechanical energy, COME, conservation of mechanical energy, to get one more equation because there are two unknowns. V is unknown and theta is unknown. I require one more equation. For that, I go for conservation of mechanical energy. Vertical circular motion, right? Usually conservation of mechanical energy works there. Okay, right. So let's see loss in gravitational potential energy. If this is theta, this will also be theta. You drop a perpendicular. This is the height fallen. Loss in gravitational potential energy equal to gain in kinetic energy. So we assume that initially it was having almost negligible velocity. Loss in gravitational potential energy is mgh, and that is equal to mgr into 1 minus cos theta. This expression would have come many times. Students somehow just remember it, half mv squared. So this is second equation. You look at these two equations, right hand side is the same. That means left hand sides have to be same. Combining these two, what I get is mgr cos theta divided by 2 equal to mgr into 1 minus cos theta. So mgr gone. Then you take a cross multiplication, 2 minus 2 cos theta equal to cos theta. If you bring it to this side, you will get 3 cos theta equal to 2. Otherwise, cos theta equal to 2 by 3. In fact, this is a formula students generally remember, 2 by 3. And once I have that right, height, they were asking about, let's call this as y because this is h. No? So then cos theta is this. Then what is this height we have? This is theta, and I want this height. This height I want. That will be r cos theta, r cos theta. So that means r cos theta is the height at which this happens, which is going to be 2h by 3. So after traveling h by 3 to the ground, towards ground, it loses contact. H by 3, it loses contact. Meaning from the bottom, it is 2h by 3. Generally, students remember it as a result. By the top, from the top, you travel down by h by 3. That is where you are going to, the block is going to lose contact there. So that's a point here. Okay. Very good. Better you remember it like a result. Next, a uniform chain of length 3 meters and mass 3 kg overhangs on a smooth table with a 2 meter lying on the table. Okay. So 2 meters chain is on the table. 2 meter chain is on the table. Okay. And then remaining 1 meter is hanging. 1 meter is hanging. Okay. Let's say this is 1 meter. So if this is 1 meter, right? This is 2 meter. Total 3 kg you have now, mass is uniformly distributed. And so 2 meter corresponds to 2 kg and 1 meter corresponds to 1 kg. Okay, fine. If K is the kinetic energy of the chain in joules, as it completely slips off the table. So as it completely slips off the table, this is the initial situation. Okay. All right. Now, whenever the bodies are moving vertically downward and you want to compare initial and final situation, draw pictures side by side. Side by side will give you a better idea of how the vertical motion is happening. So this is a picture of the situation at the beginning. You take the picture of the situation at the final stage when it is about to slip and then keep it side. So we will keep the diagram over here. So the chain is just slipping off. That means the entire chain is like this. Now it is going to have some kinetic energy. That kinetic energy they are asking. Okay. So obviously I'm going to use conservation of mechanical energy. Actually, when it is coming out, right, at this point, before entering, it is got velocity in horizontal direction. After that, it is going to have downward velocity. So there will be some impulse there to change the direction of velocity. But if you assume each bead is of negligible mass, that impulse can be neglected. So you can neglect the loss of energy during that transition phase there. So just use conservation of energy because these conservative forces are very path independent. You can go in any path to get the energy required. So what you can do is this 1 kg mass is there, no? So imagine that 1 kg mass is there only. This mass and this mass is the same. So actually it is slipping off completely, but you can rather assume that this whatever is there on the top, okay, whatever is there on the top, and that is slipping over. This part is slipping to the here. It is coming here. So this is 2 meters length, right? Of course, it is not to the size scale there. It is not to the scale. So you have more, right? 2 meters, no? No. So the center of mass of that would be at a distance 1 meter from the bottom. This is 1 meter, correct? No, 1 meter. That means from the top it is 2 meters. So what you can assume is that this particular chain center of mass was initially here. It has been transferred to 2 meters below. So there's a loss in gravitational potential energy of upper part. And how much is that? 2 kg into g into displacement of its center of mass. And that is going to be gain in kinetic energy of the entire chain. And that's all. You will get how much? K equal to 40 joule. 40 joule is the energy that you will get there. I hope you understood. So when you are dealing with the potential and gravitational potential energy, you can assume the entire mass to be concentrated at center of gravity. And for small objects, center of gravity coincides with center of mass there. So that's the idea. So you can treat this whole thing as a point mass place there. Finally, it is here. Initially, it is here. Finally, it has gone to here. What is the displacement of it? What about this part? You can assume it to be present there only. All right. I hope you understood the question there. Let's move on to the next problem. Yeah, so graph-based questions, there are many. I've just taken one of them so that you will have that idea. So I'm trying to cover questions, may not be very tough, but overall it is going to cover all the ideas that are asked in various years and so on. Okay. A particle is moving in one dimension from rest. Okay, initially it is at rest. Under the influence of a force that varies with the distance traveled by the particle as shown in the figure. Okay, the kinetic energy of the particle after it has traveled at 3 meters distance is okay. So I'm assuming that there's only one force acting. We'll use work energy theorem. Work energy theorem, Brahmastra for this chapter. This is the topic. This is the idea you can using which you can solve any problem in this chapter there. Work energy theorem. Where conservation of mechanical energy has got some conditions. Only under certain conditions. There should not be any internal dissipative forces. There should not be any external forces doing work. Otherwise, total work done by external forces plus internal dissipative forces has to be zero. Only then mechanical energy is conserved. But this is, you can apply it. Any inertial frame, you can apply work energy theorem. Even if it is non-inertial frame, you calculate pseudo force work done and you can use it. It's a very powerful tool, but sometimes it might be a bit lengthy. That's all. Okay. So how do you calculate, use the idea? Work done by this force equal to change in kinetic energy. We just have to calculate work done. Work done is nothing but integral f dx, all right, from initial to final, which is nothing but area under force versus displacement graph. This area I have to calculate. Let's call this as A1 and this area is A2. So we have to calculate the total area and substitute that A1 plus A2. Now A1 is a rectangle. Rectangle area is 2 meter into 2 Newton. So that is going to be 2 meter into 2 Newton. That is base into height. That is 4 joule. And A2 is a trapezium. Trapezium area is half of sum of the parallel sides. 2 Newton one side and 3 Newton other side. 2 Newton plus 3 Newton into separation between them, that is 3 minus 2, which is 1. So how much do I get? 4 joule here plus 2.5 joule. Totally 6.5 joule is the work done, which is equal to kinetic energy there. Initial kinetic energy is 0, final kinetic energy is that value. Okay. So I hope you got it. Next problem. A person pushes a box on a rough horizontal platform surface. He applies a force of 200 Newton over a distance of 15 meters. So he was applying continuously 200 Newton for 15 meters. Thereafter, he gets progressively tired. So that looks like reality. You can't apply continuously by the same amount of force. Yeah, so he gets progressively tired and his applied force reduces linearly with the distance 200 Newton. Okay. So the total distance through which the box has moved is 30. Okay, total 30. First 15 meters, it was having constant force. The next 15 meters, it is decreasing from 200 to 100 Newton. Okay. Now, what is the work done by the person during the total movement? So basically, you need to draw the graph. Earlier question, they gave the graph, and here we are supposed to plot the graph. Idea is the same idea. Area under the graph, we need to calculate F towards the X. Up to 15 meters, it is a constant force, 200 Newton. After that, up to 30 meters from the beginning, the force is reducing linearly to 100 Newton. All right. So that's what you have here. So we need to calculate the work done. Work done is basically area under the graph. Okay. So let's call this, divide this into two parts. Rather, you can actually take this as one trapezium. So undo. Okay. Can you see this as one trapezium directly? We can find the area of a trapezium directly. But actually here we've got a problem there. So we'll divide that into rectangle only. So this is one rectangle. Yeah, this is one rectangle. Let's call it as A1. This is another trapezium, which is A2. Okay. So A1 is how much? Base into height. 15 meters into 200 Newton. That is A1. And A2, it's a trapezium, half into sum of the parallel sides, 200 Newton plus 100 Newton into separation between them is 15 meter. Yeah. So how much do I get? This is a 3000 joule plus this is 100 plus 200, 300 divided by 2, 150. 15 15s are 225, 2250. Yeah, so you will get 5250. That is going to be the answer there. I'm supposed to leave the calculation but for you, but because it's simple, I've done it. Okay, anyway, idea is area. First of all, you need to be able to draw the graph. It's basically reading comprehension. We need to convert text into diagram. That's the most crucial skill that you require. Otherwise, it's a very simple problem there. Okay, then let's move on. Yeah, a small block starts slipping down from a point B on an inclined plane AB, which is making an angle theta with the horizontal section BC. BC is smooth. Okay, BC is smooth. Very good. I hope this picture is clear to you. B, C, A here, and this is theta. Okay. BC is smooth and CA is rough. So C is rough. This is rough. You have friction there. Very good. Coefficient of friction is mu. It is found that the block comes to rest as it reaches the bottom. So here it is at rest, and here also it is at rest. So starting from rest and going to rest. Okay, starting from rest and going to rest. It is found that the block comes to rest as it reaches the bottom. Okay, of the inclined plane. BC equal to 2 times of AC, they said. So it doesn't look like that in the diagram. Let's say BC is let's say AC is L, then BC will be 2L, no? Right? So BC is twice of AC. The coefficient of friction is given by mu equal to K tan theta. Then we need to calculate K there. So the condition, what is the condition here? It has to start from rest, and finally when it reaches to the bottom, it should have zero velocity. So the condition that I need to use, that conditional equation, is that change in kinetic energy is zero. So this is the condition I have to use. Initial kinetic energy is zero, final kinetic energy is zero, change in kinetic energy is zero. Using that, I need to calculate K. Now, kinetic energy, the moment I see change in kinetic energy, I want to use conservation of mechanical energy. Obviously, you can't apply here because it's a kinetic friction, dissipative force. You can't use it. But work energy theorem, anyway, it's a super powerful tool here in this chapter. So I'll use work energy theorem for the entire journey from A to C, directly from A to C. You don't have to split that into parts there. Okay. That is equal to change in kinetic energy, which is 0. So in that process, what are the forces acting on it, right? One is gravitational forces acting, normal reaction is acting, and friction is acting. Work done by normal reaction will be 0 because the displacement is along the incline, whereas normal reaction is perpendicular to incline. So leave it. Work done by gravity, I have to calculate. So for work done by gravity, I just have to calculate only vertical displacement. You see, this is 2L and L, totally 3L. 3L vertical component will be 3L sine theta. So work done by gravity is mg plus only because force down, displacement is also downward vertically, into 3L sine theta. That is work done by gravity. Minus work done by friction will be negative, minus mu mg cos theta into L. Right? L is the displacement of a point of application of friction there. This whole thing has to be 0. That means this must be equal. Correct, no? So mgl gone. Then what am I getting here? 3 equals to, or otherwise, let's go on with the other one. Not redo, but undo. Undo I have to do. Right. So if I take mu equal to 3 sine theta divided by cos theta. So that is 3 tan theta. That means K equal to 3. Very straightforward work energy theorem. Straightforward from B to A, you have applied, you will get it. So very, very simple problem. I hope you got it. Let's move on to the next problem. A block of mass M is kept on a platform which starts from rest with a constant acceleration g by 2 upward, as shown in the figure. Work done by normal reaction. So this particular question I have taken here because in the previous question you see work done by normal reaction was 0. But here work done by normal reaction will not be 0 because the block has displacement. The point of application of normal reaction has displacement in the direction of normal reaction. Here it does work. In the previous question, normal reaction doesn't work. So anyway, what is normal reaction here? I think students remember it like a formula M into G plus A. All right. Right. You can with respect to the platform, pseudo force will be there. MA plus MG is the normal reaction. So that's what you have. That is going to be G plus G by 2, 3G by 2, 3 by 2 mg. That is normal reaction. And then in T time, what will be the displacement of point of application? It's going up. of G by 2 into T square. This is upwards. Normal reaction is also upwards. Work done will be positive. So work done by normal reaction equal to N into S directly. So what do I get? 3 by 4 into 2. 3 by 8. 4 into 2, 8, no? 3 by 8 M into G square T square. That's the answer. Okay. Very straightforward. But conceptually, in the previous question, normal reaction was not doing work. But here it is doing work because the point of application has a displacement in the direction of force there. Okay. Next, a block of mass M lying on a smooth horizontal surface is attached to a spring of a spring constant K. The other end of the spring is fixed as shown in the figure. Okay, that is understood. The block is initially at rest. So right now it is at rest. Initially at rest, and deformation is also 0. It was having no deformation, equilibrium position. All right. If now the block is pulled with a constant force, now the force is applied. The moment you force apply, right, it is no longer going to be equilibrium position because the net force is there now. But speed will be 0. It will start from 0 speed. It can't suddenly change velocity because what force we are applying is a non-impulsive force there. So it goes on and keeps on because of the movement of the block, the spring elongates, spring force increases. There will be a position where spring force is just balanced by applied force. That's where you will get equilibrium, new equilibrium position. That's where you will have the maximum speed. And then after that, it will go on further to extreme position. So now they're asking you to find maximum speed. Where will you have maximum speed? At mean position only. This is extreme position. Yes. It's going to be simple harmonic motion, right? If you understand that it is simple harmonic motion, problem would be much easier. You don't have to use conservation of work energy theorem also. So this is extreme position. There will be a mean position. Okay, let's write it as MP. The separation between them is amplitude. All right. At mean position, we know net force has to be 0, no? That means K into A is the deformation of the spring up to that point, and that should be equal to F. From there, I'll get A. That is F by K. So I know the amplitude. Then what is the velocity maximum or maximum speed? That would be A omega. Right? Simple harmonic motion. A omega. A is F by K. And omega is root over K by M. So what do I get? F by root over K into F. That is one way to do. Of course, I can use work energy theorem also, but I think SHM idea would be much easier to handle it. So where will you have maximum speed? At mean position. Where were you initially? At extreme position. How do I know that it is extreme position? Because speed was 0. All right. Okay then. Yeah, a spring whose unstretched length is L has a force constant K. The spring is cut into two pieces of unstretched length L1 and L2. L1 equal to n times of L2 and n is an integer. The ratio of the corresponding force constants is. So it's a very simple, straightforward. I think this problem can be asked in CET exam also. Very, very simple idea, but I thought to revise it because it's an important idea. Many places it might be useful. Right. So when you have a spring like this, okay, let's say one big spring is there of natural length L. You can visualize it as two springs. All right. This is length L1 and this is length L2. So that L1 plus L2 equal to L. I'm just trying to explain that concept there. Okay. Now when you are stretching it, right? Let's say it is elongated by E1. This is elongated by E2. Total elongation will be E1 plus E2 is the total elongation. All right. Now you see that L1 proportional to E1 or L2 proportional to E2, L proportional to E. More the length, more is the elongation. You have more the number of rings you will have it. But because these two springs, let's say the spring constant is K1 and this is spring 2, they are connected in series. Whenever the springs are connected in series, tension has to be same. So whatever tension you have here, T1, the tension here has to be same. So T1 equal to T2. That means K1 E1 K1 E1 must be equal to K2 E2. Okay. But E is proportional to L. No? We can also write it as K1 L1 that is equal to K2 L2. This is the idea you need to remember. K1 L1 equal to K2 L2 equal to K effective into L. This is something that you are supposed to know. They're asking K1 by K2, which is going to be L2 by L1. Very simple. K1 by K2 equals to L2 by L1. And what is L2 by L1? L2 by L1 would be 1 by N. That's the answer to you. Very straightforward, but just to revise that concept there. Okay, right. Next problem. A uniform cable of mass m and length L is placed on a horizontal surface such that its 1/nth of a part is hanging below the edge of the table. To lift the hanging part of the cable up to the surface, the work done will be, earlier we have done slipping situation, now it has to be lifted up. So it's just a reverse process. Let's say you have some cable is there. I'm just mentioning it like this, cable or chain, whatever it is. And hanging part is 1/nth. 1/nth part is hanging. So that means L/nth part is hanging. Mass of it also would be N/N only. Correct, no? Because mass is proportional to length there. And where is its center of mass located? So if I have to take some other color to just to indicate the center of mass of this hanging part, and that would be midpoint. No? So L/N/2, L/2N. So while calculating work done, while calculating potential energy, you can assume this entire part to be located here. Now, when you are pulling it up, the center of mass has to go up. All right. I need to supply work, I need to supply energy or do work on it so that the center of mass goes up. Entire chain goes up, meaning center of mass goes up. So the work done by that external agent will be equal to increase in potential energy. That is, mass is m/n into g into height raised by center of mass is L/2n. And so you will get mgl by 2n square. That is the work done that's needed to pull it up onto the table. That's a very straightforward problem. I hope you understood that. Let's go to the next problem. Right. A particle is moving in a circular path of radius under the action of an attractive potential U equal to k by r square. Its total energy will be. All right. So U they had given k by r square. Attractive potential, they said U equal to k by r square. Generally, attractive potential will have negative value. So I'm assuming that k itself is negative. All right. Potential energy will be negative for a bound system usually. So, but they didn't mention that, but I'm assuming that k to be negative. Anyway, so I want the total energy equal to potential energy plus kinetic energy. Potential energy they gave it, but I need to calculate kinetic energy. How do I find kinetic energy? How do I calculate kinetic energy? So you would have seen that in vertical circular motion also, from kinetic energy to centripetal acceleration, there is a link. There also you get mv square, and here also you require mv square. From centripetal acceleration also we can calculate it. Immediately you should get that idea, centripetal acceleration related to kinetic energy. So what I do is I'll calculate the force here. Force will be equal to minus du by dr. Correct, no? Central force corresponding to any potential is this. So what do I get? Minus of k into r power minus 2. Differentiation will be minus 2 by r cube. So you will get 2k by r cube. This is going to be the force there. So this force must be equal to mv square by r. All right. This force must be equal to mv square by r. But now the point here is my problem in this particular question is obviously mv square by r is positive. That means this should be positive, meaning k has to be positive. All right. If k is positive, then potential energy will be positive. When you have potential energy, it will be repulsive force there. So that is a challenge we have. K is supposed to be negative. So that's a challenge we have. But anyway, whatever is given with that, if we have to discuss, probably for JEE advanced preparation later on, we'll take that point and cover it. So this is a force we have it. R gets cancelled. All right. Then half mv square from here I can calculate. That will be 2k by r square. All right. So now if I want to go accurately, what I would like to do is I'll put a minus over here because k is negative according to this. So in that case, total energy will be k by r squared minus 2k by r squared, and that's going to be minus k by r squared. That should be the energy that we are getting. But anyway, that sign difference is there. So I hope you understood the point there, but that's how we can solve this problem. Okay, then let's move on with the, I think I have done a small correction here by 2, no? 2 gets cancelled. That means this is also gone. You are supposed to get 0 in that case, all right? But I'm not sure if they had given 0 here. That's a trick challenge you have. If you take K to be negative, you'll get 0 is the energy. Anyway, so I hope you understood the point there. Let's move on. Little bit of controversy in this question. Let's go on. An object is dropped from a height h from the ground. Every time it hits the ground, it loses 50% of its kinetic energy. Meaning if it loses 50% of its energy basically, so that means it will go only half the initial height. The total distance covered by it as t tending to infinity is total. Okay, I think you will get a GP series here. So this kind of problems suggest that only. So anyway, we drop from certain height. So it falls by a height h and then rises, and because it is losing 50% of energy, it can go up to h by 2. After that, it is going to fall back. See, I'm showing it sideways because showing here itself will make it clumsy. So it will fall down. Doesn't mean that it is going sideways. It is just going only in one dimension there, right? So it will come here. After that, it is going to have one more hit. Then it will lose further 50% of whatever is left. That means it rises to only h by 4. Then further it falls back to h by 4. All right. Then next collision, it will go to only h by 8 and so on. Right? You will get a geometric series like this. So the total distance they are asking, not the displacement, total distance. First distance is h. After that, h by 2 and then h by 2. So that will be 2 times of h by 2. The next series will be 2 times of h by 4. And then h by 8 plus h by 8. 2 times of h by 8 and so on. It goes on like this forever. All right. So what do I get? This is the total distance h equal to, let's call it as L, total distance h plus h by 2 plus h by 4 plus and so on. So h plus, this you can write as h into 1 plus 1 by 2 plus 1 by 4 and so on. It's a geometric series you have. A by 1 minus r. So 2 you will get, that means 3h is the total distance. That's the answer you have, very straightforward. It's more mathematics than physics here. Okay, next. A point particle of mass m moves along the uniformly rough track PQR. So PQR is a rough track. Okay. And what are they saying? The coefficient of friction between the particle and the rough track is mu. The particle is released from rest at point P. So here velocity is 0 at rest. Okay. Very good. And then from point P and it comes to rest at point R again. So it will be coming to rest again. This is also rest. That is change in kinetic energy 0 for the entire journey. Okay. Now they said the energies lost by the ball over the parts PQ and QR of the track are equal to each other. So it is losing same amount of energy. Energy lost by the ball. What energy is it losing as it is coming down? What energy it is losing? It will be losing gravitational potential energy. What is the gravitational potential energy we have here? mgh, no? In that 50% is lost from P to Q and then 50% is lost from Q to R, it says. That's what he's saying. So why will it lose energy? Because of dissipative force there. Kinetic friction is there, no? So because of kinetic friction, it is losing that. All right, very good. And then they said, and no energy is lost when particle changes direction from PQ to QR. Yeah, that's important actually. So as it slides down, right, suddenly changing direction of motion, you will have a collision there. So he's saying that you neglect that collision. Don't worry about that collision. There's no loss of energy as it is sliding and then suddenly changing the direction of motion there. Now the value of coefficient of friction we need to calculate, and also x value they are asking you to calculate. Okay. So a little bit of geometry here. See, this is 2. This is 30 degrees. How much is this distance then? 4 meter, no? 4 meter. And what about this distance? All right, 4 cos 30. This will be 2 root 3 meters. Okay, 2 root 3 meters. And they said QR, no? QR is x. X is there. Very good. Now, loss in gravitational potential energy. Right? Loss in gravitational potential energy. That is mg into h. That will be equal to 2 times of loss in energy from Q to R. We can write now. Because they said 50%. 50% here, 50% here. So Q2 or whatever it is losing, that is going to be 50% of mgh. So that means mgh equals to 2 times of mu mg into x. Mu mgx is a work done there, negative of mu mgx. I'm just taking the magnitude on there. Loss already mentioned. No? So from there, if you look at mg cancel out, I will get x. X is equal to how much? H by 2 mu. H they gave 2 meters divided by 2 into what was mu they had given? Mu they have not given. So you just take it for that as it is. Okay. Mu we don't know. Keep it aside there. I need to calculate mu also. That means 1 by mu is x there. So to calculate 1 by mu, that mu there, I'll focus on PR. Work done by friction in PR. And that is going to be minus mu mg cos theta. That is frictional force into that length, whatever is the length. Alright, let's call it as L or otherwise 4 meter. 4 meter, no? 4 meter, you have it. This is going to be work done by friction as it goes from P to Q, PQ. Alright, and that should be equal to mgh by 2 again, minus of mgh by 2. So if you remove mg and then mg and minus gets cancelled, I think you will get mu from here. How much will I get mu? Mu equal to h by 4 2s are 8 cos theta. That is what I have. You can substitute. H is 2 by 8 cos 30 is root 3 by 2. So you will have 2 getting cancelled out. Then you have 4 1 by 2. 1 by 2 root 3 is what I am getting. 1 by 2 root 3 is this. Very good. So mu equal to 1 by 2 root 3. If I substitute there, what will be the x value I will get? X is equal to 2 root 3. And very interestingly, you can see this is 2 root 3 and this is also 2 root 3. Very interestingly, and it's actually a very important question. And so the work done in this particular case by the friction depends only on horizontal displacement, not on the displacement in vertical direction. It's a very important question from Irido. So I'm sure it have been discussed in your class somewhere. So work done by friction will depend only on this. Work done by friction will depend on this. When it is doing same work, right? It is 2 root 3, this also should be 2 root 3. Directly you could tell. X equal to 2 root 3, you could tell them. Because it should do the same amount of work, meaning same displacement horizontally. That's also another way of doing it. And of course, we got the idea. I hope you understood it. It's a very important question. I hope you go through it again and make sure that you are comfortable with this particular idea. Right. A particle is moving in a circle of radius r under the action of a force F equal to alpha r square, which is directed towards the center of the circle. Okay. Total mechanical energy we have to calculate. Same idea here also. So they gave force. When they give force, right, I can find potential energy. I can use F equal to mv square by r, and from there I can calculate kinetic energy. And then finally potential energy and kinetic energy, you sum it up, you will get the total energy. That's a roadmap basically. From force to potential energy, I'm sure you are aware of that, right? Potential energy equal to minus integral f dx, fdr or fdx. And F equal to mv square by r, from there I can calculate mv square also there. You can write Fr equal to mv square by 2, you will get half mv square also. That's all. So first to calculate, integrate it, what do I get here? This is minus alpha into r cube by 3. That is going to be potential energy. And kinetic energy Fr by 2. Alpha r squared into r, that will be alpha r cube by 2. That is going to be the kinetic energy. Total energy is the summation of it. So alpha r cube by 2, that is kinetic energy. Alpha r cube by 2, that is going to be kinetic energy, minus alpha r cube by 3 is going to be potential energy. That is the total energy. So if you calculate, what do I get? Alpha r cube by 6 you will get. That's the total energy you have it. They said that potential energy is 0 at r equal to 0. You can assume that. Right. So I think we have completed this particular slide here. I hope you got the idea. I try to cover as many ideas as possible, which are easy and then very important for your examination, like last minute preparation, taking PYQ as the basis. So with that, I'll conclude here. Thank you very much for your time. Until next time, goodbye. See you.